All right, we're going to get started. Okay, so tonight we're actually going to learn a technique of integration. So we're going to look at the topic tonight called integration by parts. And we'll bring the integral test back a little bit later. But Calculus 1, you learned all the derivative rules. Maybe there were 15 of them, and you memorized them. It took maybe 3 weeks at most. And you were able to find the derivative of every function. Towards the end of Calc 1, you then found some antiderivatives. And as I've been mentioning all along, integration, anti-differentiation, is much, much more complicated than differentiation. And what I mean by that is that there are so many more rules, so many different tiers. And then when you've exhausted all the different algorithms, you sometimes can't find the antiderivative algorithmically using elementary functions, in which case we'd have to bring about power series and estimate with the fundamental theorem of calculus with the integral from a to x or something like that, f of t dt. And that was what you did in Calc 1. In Calc 2, we used Maclaurin series to find antiderivatives, and that was on your midterm. I'm returning now to more traditional methods for finding antiderivatives. And we could actually have a whole course on finding antiderivative rules. We could do a new antiderivative rule every day for the rest of the course and still have so many more to do. But most Calc 2 courses don't do that anymore. There's a whole table of integrals. It's this big 1,200-page book that has all these antiderivative rules in it. But we basically just cover the most prevalent. Use substitution at the end of Calc 1 was, of course, a big deal. And integration by parts is going to be a pretty big deal as the other big technique of integration. And some of you may have seen it before, but for all intents and purposes, it's the backwards product rule. So it's the backwards product rule. So it really comes down to a rule, and the rule I'm going to talk about it right now that we use is the integral of u dv is equal to uv minus the integral of v du. So just take a moment here. This is going to be the most important formula of the evening. And it is called integration by parts. And it's integral of u dv equals uv minus the integral of v du. Essentially, this is the product rule from Calc 1, fg, which was gf prime plus fg prime. And then we essentially just here used u and v instead, and we went backwards. The proof is in your ebook. It's pretty short. I'll skip it over here, and we'll just start applying the rule in a moment. So what this basically means is you need a u and you need a v. You need to identify them, and you would try to find the antiderivative. So I'm going to jump right in here to an example. So one of the ones we're going to look at right now is the integral of x cosine x dx. So here we're looking to find the antiderivative of a product. And well, of course, you could use power series to do this. We could use Maclaurin here. We don't need Maclaurin because this does have what we call an elementary antiderivative. You just can't do it by use substitution. This is a classic example of something that will not have use substitution doing the trick. So this is a product. You have x times cosine x. So what we want to be able to do here, I'm going to go back and say u dv is equal to uv minus the integral of v du. That's the formula. And our question was the integral of x cosine x dx. And what we want to be able to do here is identify a u and a dv. So when you take a look here, you can see that the first guy we'll call u, and the second guy we'll call dv. According to the formula, you're going to need to find the u and the du and the v. So what happens now is actually pretty nice. We make a table, or at least I do, and you have a u, and you have a du, and we have a v, and we have a dv. And all I do is plug in what I just established, which is that u is equal to x, and the dv is cosine x dx. So we have u as x, and we have dv as cosine x dx. Well, our job now is to find the v and the du, and then plug directly into the formula to find the antiderivative. So u is equal to x. So if you want du is just the derivative 1, but du has to match with a dx. Differentials have to come with differentials. The d something has to come with the other d something. So u is equal to x, du is 1 dx. And then moving over here, dv is equal to cosine x. So you have to go backwards now to find the v. So if the derivative is cosine x, well, the v here has to be sine x. No plus c or anything here. We don't need that yet. So the good news now is that you can just plug directly into the formula and proceed from there. So what we're going to do next is we go back and we say integral of x cosine x dx is equal to uv, which is x sine x, minus the integral of v du. V du is sine x dx. So I have uv minus the integral of, I call this, by the way, I have a nickname for this topic. I call it voodoo, because it's integral of voodoo, vdu. So sometimes I'll refer to this as the non-technical name voodoo. So we have x sine x minus the integral of voodoo, which is minus integral of sine x dx. You can get the right answer right now if you can find the antiderivative of sine x, which of course you can. So we're about to get our first answer by integration by parts in this course. And what we can do now is just come up with x sine x, and then the antiderivative of sine x is negative cosine x. So the integral of sine x dx, you're talking about minus cosine x. There's already a minus here, so that's a plus cosine x. And we have plus c. You have found the antiderivative. The backwards product rule, integration by parts, voodoo. If you don't believe the answer, you can always do a quick product rule from Calc 1, add cosine, and you will in fact get x cosine x as the simplified answer. Any questions so far? This is the procedure. Almost the whole night will really be about this and just practicing this skill. So this is a very different week than it was last week, which was pretty lofty and conceptual. This week is pretty mechanical. And it is an important technique of integration, and we'll see some different kinds of examples as we go through the night. Any questions to start us off? Okay. So let's try one. Okay, so let's try one here. So suppose we have integral of x squared ln x dx. So integral of x squared ln x dx. So this is another case where we have an integral of a product, and u substitution is just not conducive to getting an answer here. Letting u equal one of those two things and using u substitution will not yield anything. The only caveat in this question is you've got to be careful about what you choose as u. So just a little rule of thumb here. Even though x squared is coming first, it behooves you to let u equal ln of x here. So in the voodoo integration by parts process, the log is usually a better u. So you could try it the other way and you might not be so successful, but letting u equal ln of x is usually a good way to go. So letting u equal ln of x is what my recommendation would be. So you'll very rarely see it this way. It just doesn't look right. You often see it the way I presented it, but for integration by parts purposes, you want to switch it around. So I'm going to stay quiet now because you're going to do your first ever example in this course on your own. So you're going to have u and you're going to have dv. So you're going to make your little table now. And some students have their own ways of doing this, something called tabular method or some other tricks. You can do that too, as long as you get the answer for this. That's what I care, and showing work, of course. But I care more about your way of getting the antiderivative and ultimately getting the correct antiderivative. So you're going to try this question. U is going to be ln of x here. And dv is going to be x squared dx. And you're going to proceed in the chart and then directly to the formula. So let me give everybody about 5 minutes or so. See if you can come up with an answer.
Ebron, I have a question.
Yeah.
If it's possible, could you explain very briefly like why this rule works, how you did for the McLaurin series, or is that if it's too complicated, then never mind?
It's not work. I mean, try the way I'm really doing it tonight, and it's not hard. It's just a reversal of the product rule and moving everything over. What I want you to do is just take a look if you have the ebook at the beginning of 5.6, and they give a few line proof. So this particular, I'm not going to do it in class tonight, but if you have questions about it after you read it, I'll be happy to go over it with you. But just try reading. It's a few lines, and it's just a quick proof of why the technique works.
Okay, thank you.
Sure.
Could you repeat the section again?
5.6 in the ebook, integration by parts.
Thank you.
Okay, so here we have the u is ln of x. So the du is 1 over x dx as the derivative. And the v here, if we go backwards to find the antiderivative, is x cubed over 3. So once we do this, we go directly to our formula, which is uv. So the formula is uv. So we put x cubed over 3 ln x minus the integral of voodoo. Now let's take a look at voodoo here. X goes into x cubed, x squared times, and then it's easier to pluck the 1/3 out of the integral symbol. And then there's a dx. This puts us in position now to find the antiderivative. So you have the x cubed over 3 ln x. And then here you have an antiderivative x cubed over 3, but you're multiplying by 1/3, so you have x cubed over 9. And then you have your plus c right here. So you have successfully found the antiderivative using this technique right here. Any questions about this?
Wait, I got something different because I thought it was v du, so I did x cubed over 3.
Yeah, it should be x cubed over
3 times du, right? So isn't it x cubed over 3 times x squared? So x to the 5th over 3.
Well, let's see if I could have made a mistake. uv minus.
I got x to the 6 over 18 though.
Well, let me see what happened here. So we had u was ln of x, and then the dv was x squared dx. So we did the antiderivative rule here. And we then decided to do uv, which was these two together, so that checks out, minus the integral of voodoo. Putting voodoo together, when you put the voodoo together, which I'm going to do right here, it's 1 over x cubed over 3. So when I put the voodoo together, I simplified. X goes into x cubed, x squared times. So it's minus the integral, or 1/3 the integral of x squared. Then what I did was I found the antiderivative here, which becomes x cubed over 3, but you're multiplying by the 3 on the outside, giving us x cubed over 9. Does anyone agree with my answer?
Yeah, I
Yes,
just
that's what I
got
got.
Yeah, I got your answer too.
Yeah, so I think the problem is, I think, and I want to just accentuate that in this problem, when you put the voodoo together, you want to simplify it before you find the antiderivative. That's the key. All right, we're going to practice more. We're going to practice more. So what happens? What happens now when we get to this one? Integral of x squared sine 2x dx. All right, this is going to keep us busy. So this is the integral of x squared sine 2x dx. I guess you could put the 2x here in parentheses if you choose. Okay. So there's no reason to do the commutative property here. The way it is fine. The way it is fine. You don't have to reverse it. There's no natural log. So we'll go here for the u. And we're going to definitely be busy in this problem. So we let the u equal x squared and the dv sine 2x dx. Okay, I want to just say a couple of things here. Du is easy, you're going to do that. The v is technically found by using u substitution because it's sine of a linear function. However, if you use u substitution here, this problem is going to become overly cumbersome. So you've got to be able to go backwards pretty fast. So to go backwards here, I call this like a baby u substitution. You've got to know that the antiderivative of sine of linear is negative cosine of linear. So antiderivative of sine of something is negative cosine of that something as long as it's linear. However, because of the u substitution, you have to put the reciprocal of the linear coefficient in the beginning. That's a quick way of going backwards with sine of linear, e to linear. It's too much to do u substitution. It's too babyish, if you will. If you want to prove it right now, just once and for all, let u equal 2x as u as it is in u substitution, and prove to yourself that it becomes this. But it's good for you in this course to now know, and especially future courses, sine of linear goes back to negative cosine of linear, and you just put the reciprocal of that guy in the front. Now take it away, but you're going to notice you're going to be busier than the last couple of times. So let's let tonight be as much of a workshop as it is a lecture. So let's see what you can do here.
I have a question.
Yeah.
Could you put sine 2x as u and then put du as 2 sine x cos x, or would that make it too complicated?
Well, it probably would make it too complicated, but there are cases, and let me say a couple of things about integration by parts. Sometimes you can go either way with the u and the dv. There's usually easier ways to proceed. Sometimes one way is a dead end. Sometimes there are integrals where you could do u substitution or integration by parts. So I often say that integration is not cookbook rules. It's more of an art than it is a bunch of rules. So it kind of takes a little bit of practice and getting used to. So all I can tell you is from experience, to use my favorite word again, it behooves you when you have the x squared in front, if you can use the x squared as u, that's the way to go. And number two, you couldn't because the natural log is problematic.
Okay, thank you.
But it's always fun. I remember learning this the first time. It's fun to try it the other way and see what happens. So let me let you try for a little bit. And my goal is in every problem tonight to show you something different that happens. I'm going to build on our themes and we'll see something slightly different in each problem. So you're noticing what happens in this problem. Or maybe not. Anybody noticing anything?
You have to do the integration by parts twice.
That's the key in this problem. So we have to be careful with the parentheses. So in just another moment, I'm going to take you through the end of this so you can check your answer. And then we move on to another problem. Keep in mind that we're still in the middle of our story, and the story is going to conclude next week. So we're still in the middle of that. Basically, the whole course is the story, as I call it, one more week next week. And then we do 2 standalone topics before Thanksgiving, and then 1 review for the final right after Thanksgiving. Actually, we'll do a review in class, and then I'll do a Sunday review like I did last time. All right, so du is 2x dx. So let's go here. uv, putting that together, negative 1/2 x squared cosine 2x minus the integral of voodoo. Now the minus has a negative there, so it's better to put plus integral of voodoo. But just be careful when you put the voodoo together. The minus negative is a positive, and then the half times the 2 is going to go away. So we're just going to wind up now with x cosine 2x dx. So now we have the job of actually doing integration by parts again, and then coming back over here to fill in the final answer. So moving to another slide, we're going to have to do x cosine 2x dx all over again. So in order to do this, once again, u is x, dv is cosine 2x dx. So with the u being x, the du is 1 dx. And going backwards here with cosine 2x, we have to find the antiderivative using u substitution, but it's what I call the baby u substitution. Antiderivative of cosine linear is sine of linear. And then we're just going to put the 1/2 on the outside as per the rule I just alluded to. So now we have that, and I can go directly for my uv. So uv together is 1/2 x sine 2x uv minus the integral of voodoo. So now when I do minus the yeah.
I don't see the writing coming up.
Neither do I.
Yeah, I think it just went away. So that's bad. Yeah, this is an ongoing problem when I use the screen for a couple of reasons. So what's going to happen is I'm going away now, and then I'm coming back, but I think things are going to be disappearing again. So let me see if there's a way. I don't think there's a way here. All right, this is not going to be good. You can hear me, right? You can hear me?
Yeah.
Yes.
Yeah, so let me see. Now we're having technical difficulties, and it's not even because of the weather. Okay, so let's see what's going to happen here. All right, I'm going to have to go off, and then we're going to have to come back on again and see what happens. So
Is it possible to read the answer out?
well, okay, so what I can do is, hold on a second here. 1/2, if you can write, it's going to be difficult, but I guess, can you see my words writing, or you can't? Can you see the transcript?
Yes.
Okay, so 1/2 x sine 2x. This isn't going to work. So let me try. All right, we're going to have problems unless I'm going to just for the end of this problem, and then I'm going to reboot. But just for the end of this problem, I'm going to go back to my regular board, the whiteboard, just for this problem, so we don't lose it, and then we'll figure out what we're doing. So let's go for the house tour, and then we'll finish this problem. And then I'm going back to this again. So can you see the board? Yes. I need a verbal.
You're still screen sharing.
Yeah,
Yeah.
you're still screen sharing.
Everything is going catastrophically. Okay, let's see here.
Why don't we just use Google Meet from now on? That's your.
Well, no, I mean, no, that's a whole other story, but that's a whole other story. There's a whole story behind this. I have to figure this out. It's just, it has to do with something that for this course, but I don't want to, I have to figure out how to do something. I don't have this problem on Thursday. It's only on Tuesday. And I'm trying to work around the issue. So let me see, screen sharing. All right, I'm coming back to this. We'll come back to it. If I have to do the whole problem again, I'll go fast. I'm logging off and then I'll log back. I'm logging off. So we're going to start again.
If you can't stop the screen share, if people pin you and then drag the sidebar to enlarge it, you can see your camera much bigger than the whiteboard.
Okay, I just think I think without causing a whole big to do, I think I'm just going to log off and then log on, and then we'll figure it out. Okay, so let me just, I'm literally, you may have to log off and then log on. I'm not 100% sure, but let me go off and then we'll figure it out, and then we'll get back to our regularly scheduled program here. All right, I'm back. All right, so going back to this question, integral of x squared, I'll be as fast as possible here, x squared sine of 2x dx. So this is the question we had, and we already did, I'm just going to do this fast, this is the part we did, u is equal to x squared, dv is equal to sine 2x, du is 2x dx, and the v was, in this case, negative a half cosine 2x. Then we did the uv, so we had negative a half x squared cosine 2x. It's the uv minus the integral of u, which came out to be the integral of x cosine 2x dx. And then I moved to the next slide, and I was in the middle of doing x cosine 2x dx. I was in the middle of doing that. And then I have u is equal to x and dv is equal to cosine 2x. This is where things went awry. du is equal to 1 dx. And then v, the antiderivative by this little baby u substitution, was 1/2 sine 2x. Then I went right to the uv, so that's the 1/2 x sine 2x, uv, minus the integral of vu. So that's minus 1/2 integral of vu, so that's sine 2x dx. Well, now I'm still not done because I've got to handle this integral, which is that baby u substitution that I keep talking about. So here, the antiderivative of sine of something is going to be negative cosine, so it's going to be plus negative negative. So antiderivative of sine is the negative, so negative negative is the plus, but then we're going to wind up doing that linear thing again. So another half comes on the outside for 1/4, and then we wind up having 1/4 of cosine 2x. So this whole answer here, and by the way, there's something called the reduction formulas that's another way of doing problems with trigonometry in this topic. So now what I have to do is essentially take this guy and really plug back into the answer. So here comes the final answer. The final answer is just going to be negative 1/2 x squared cosine 2x plus, and now I have that whole answer that has to be filled in here, plus 1/2 x, we're just replacing that, 1/2 x sine 2x. So again, this whole answer is getting plugged in here, 1/2 x sine 2x, plus 1/4 cosine 2x. And don't forget our friend plus c. So this is a nice piece of mathematics here, giving us the antiderivative.
Can you explain how you got the 1/4?
Yeah, sure. So the 1/4. So what happened here was when you find the antiderivative again, it's that linear rule. So you have the negative a half on the outside. The antiderivative of sine of something is going to wind up being the negative cosine of something. But again, that linear rule puts the half right here. So then what winds up happening is you have the negative a half plus times the negative a half rather, which is plus a quarter. And that's how I have the cosine, quarter cosine 2x.
Thank you.
Sure. Okay, anybody else so far? So this is like a standard exam question. Go ahead.
Wait, are you gonna add the negative x squared over 2 cos 2x from the beginning? Or what out of that one?
Did I forget that? No.
Because isn't this integral that you did part of the other one?
So here's the final answer. Right, I went back here. See it?
Oh, okay, I'm sorry.
Sure. So what I put here in the purple is the final answer. Okay. So let me go to another question here. All right. This one makes me laugh. So you
didn't see the answer. Can you go back to it for just a second, please?
Of course.
Thank you.
So there, no problem. There's the answer.
Thank you.
I just had a question about when you put the plus C. So you see in the screen, after you finish doing the second interval by part, you didn't put plus C in the answer.
Yeah, and I'm glad you said that because there's too many C's and they all combine together to give you some other C. So it's customary in an integration by parts problem collectively to just put the plus C at the end, the very, very end.
Okay, thank you.
Okay. So let's go on to an interesting question. So there's something funny about this question, but I'm not going to say too much. Oh, I won't say anything, nothing. And I want to see what you can do with this. Integral of e to the x sine x dx. So this is all you. And you can tell me what the problem is. You can tell me the issues. This is a nice little problem-solving exercise for us.
Beeman?
Yeah.
If you don't mind, can you just go to the part where you did the half sine 2x dx for the integrated? Yeah.
Sure. Those of you who are working on the problem, it's the integral of e to the x sine x dx.
Okay, I got it. Thank you.
Sure. So you're trying this, and this is, this is the beauty of doing this topic for the first time. Getting stuck is okay because that's how we learn. And sometimes you get stuck and we find that you can't do anything. That happens in integration. You can prove that there's nothing to be done. And sometimes in other areas of math, we just haven't found a solution yet, like the Riemann hypothesis from last week. So let's see how you can do here. Integral of e to the x sine x dx. What's happening? Disappointed?
E to the x is a derivative of itself, an integral, so it just keeps on going forever.
Let's take a look at this. So let's see. Integral of e to the x sine x. So what we're going to wind up doing here is we wind up letting, I guess you could try u as e to the x. We can try that. We could try it. And then we can make our little table. Let's see how it goes. Du is e to the x dx. And then, of course, the u du and the v dv. dv is sine x dx. And then the v winds up being antiderivative of sine is, of course, negative cosine x. Okay, so that's an initial attempt. We'll see how it pans out. So it winds up being here. So integral, and watch how I write this. Integral of e to the x sine x dx, that's the question. Here comes the answer, is equal to the uv. So uv is going to be negative e to the x cosine x minus the integral of voodoo. So that's plus the integral of voodoo. Okay, so there you have that so far. So this was a reasonable attempt, and now you're stuck with a new integration by parts here. So I'm going to stay on the same slide here, and I'm going to try again now with the integral of e to the x cosine x dx. I'm going to try this guy. So what I'm going to wind up doing now, in similar fashion, u is e to the x, du is e to the x dx. The dv is going to wind up being cosine x dx. And then the v comes out to be sine x. Okay, so what we wind up having here now, and this is where things get crazy, what we wind up having now is the integral of e to the x sine x dx is equal to negative e to the x cosine x. And now we're going to do the integration by parts all over again. So uv is going to wind up being, so we have plus the uv, e to the x, I'm doing this part right here. uv is e to the x sine x. And then, of course, it's going to wind up being minus the integral of voodoo, which is e to the x sine x dx. So I just need to rewrite this because it got a little bit crazy here. So let me just, if you don't mind, bear with me. Did we lose anything here? No. Let me just squeeze this in here. Okay. So what wound up happening here? What seems anticlimactic to us? What seems like it's a dead end?
Because the what's on the other side of the equal sign is also on both sides, you could just move it over and then divide by 2.
That's the trick. So some people find it upsetting to get the same thing back again. And you're like, well, I'm going to go in a vicious cycle. But if you write the original question here and you keep saying what it's equal to, we do exactly what you suggested. So the trick right now, and this is the exciting part, the fact that the same integral came about again is not so terrible after all. So good answer. Just bring that integral over to the other side, and then we wind up getting 2 integral e to the x sine x dx is equal to just negative e to the x cosine x plus e to the x sine x. Now you actually have the answer, and that was very clever. Divide both sides by 2, and you found the antiderivative. If you want to make it a little bit nicer here, of course, you put the plus c. I'll leave that for you. The whole idea now was to just see that you get it again and rejoice in the fact that you can use the algebra to literally solve for the answer. Questions about this?
I'm confused how you got like the 2 again. Like the
So the 2, what I did right here, right over here at the end, once I wrote it out the way I did, I added the integral of e to the x sine x dx to both sides. That cancels this guy, and I add it to the other side. When you add it to the other side over here, how many of them are there?
Okay, 2.
Right, and then I can then just divide by 2, and that allows me to solve for the integral that I'm seeking. Questions?
B-boy?
Yeah.
So if I like assign the first equation, like e to the power x sine x dx, to a variable like maybe I, and then work with it, is it fine?
Yeah, if that helps you through, yes, you can do that. Sure.
Thank you.
Absolutely. Okay. So now a surprise, little surprise here. So just when you think integration by parts could be over, it winds up being helpful in a place that you may have not even thought it could be helpful. So take a look at number 5 here. A surprise. Integral of ln of x dx. So we knew from calculus 1 that the derivative of the natural log of x is 1 over x. We never had a function that we knew whose derivative itself was natural log of x. And at first it would seem unlikely that Voodoo would be able to work on this. But in fact, for logarithms and inverse trig functions, all by themselves, not even looking like products, Voodoo winds up doing the trick. So take a leap of faith with me. Call this first guy U, and call the second guy here dv. And take a leap of faith with me and watch how spectacular this is. So you let u equal an ln of x, and say dv is equal to dx. Now don't get too excited. This rarely works. But I'm claiming in the case of the natural log and also inverse trig functions, which we'll treat in just a moment, this works like a charm. So take a moment here, and it'll be a very simple integration by parts Voodoo question. So see what happens. All right, so this is pretty good here. This goes pretty fast because du is equal to 1 over x dx, and then the antiderivative of 1 is just x. So going right for the formula uv minus the integral of v du, we wind up getting here x ln x minus the integral of Voodoo. When you do the Voodoo, there's x and 1 over x canceling, giving us just integral of 1 dx. Coming up with x ln x minus x plus c. I actually memorized this as an antiderivative. It's sometimes helpful to know that the antiderivative of ln of x is very nicely x ln x minus x. Any questions here? So in number 6, another nice surprise. This one's a little bit harder. So the integral of the inverse tangent, and of course, by the way, these are, remember, inverse tangent and arctangent are the same thing. There's just 2 notations. Those are the exact same problem. So integral of arctangent x or integral of inverse tangent x. Another case where it would seem that integration by parts would not do the trick. Here we actually can do this. So again, the leap of faith, u and dv. Try this. There's definitely a harder component to this problem, but fight through it. So this one I'm going to give you a little bit longer on because the second part of the problem is going to take you somewhere.
Wait, I know the derivative of tan x. I know it's secant x tan x, but I don't know arctan. Is it cotangent?
No, so first of all, tangent x's derivative is secant squared x. The one you gave was the derivative of secant, which is secant x tan x. The derivative of arctangent x, you need to know, is 1 over 1 plus x squared. So the derivative of arctangent x is 1 over 1 plus x squared. Yeah.
Can you go to question 5 again, real quick?
Yeah, sure.
Thank you.
Sure. So let's see if we can do our work here. So those of you who have moved to the next part of the problem, what do you notice has to be done in this problem at the end?
A U substitution.
Right, there's a U substitution component at the end of this problem. So everybody try that. I'll give you a few more minutes.
Professor?
Yeah.
Could I ask like what the integral of like 1 over 1 plus u is?
Well, that's not coming up in this. Oh, well, yeah, it might. So if you were doing it that way, it is a natural log of the absolute value of 101 plus u. So if you were doing just exactly what you said, the integral of 1 over 1 plus u, exactly what you said, is ln of the absolute value of 1 plus u. Tonight, like I said, is very mechanical, but next week it'll be, as I wrap up the story next week, it'll be more conceptual again as I tie everything together for us. The following Tuesday, we will look at a standalone topic. Really, it's actually the prelude to Calc 4, not Calc 3. I know that sounds strange, but the following week we'll do something called differential equations, a whole separate story. It's really the story of Calc 4, but it's traditional in the United States to cover just a tidbit in Calc 2. And then the last lecture, the week of Thanksgiving, I will cover a standalone topic on volume, which in some ways is related to what you would study in Calculus 3 if you take that course. And volume, some of you did in AB Calculus in high school or a course prior to this, but I'll put my own historical spin on it with a few fascinating derivations. So that's what we have coming in the next month or so. All right, so let's get to work. So again, nice surprise here with integration by parts. U is arctangent of x. Du is the famous derivative 1 over 1 plus x squared dx. Then we have dv is equal to dx, and v is equal to x. So going right here to our uv, so we have x arctan x minus the integral of x over 1 plus x squared. So right here is a good time to use u substitution. So I know you were thinking of, somebody in the class was thinking of making this the u, the x squared, but the way I would proceed personally is to let the entire denominator be u. So this is a different u than the u we just used. Sometimes people would call it w, but I'll allow you to use it u because I know what you mean. So in this case now, what I'll do in the next problem, I'll just pull this here and I'll just review and do a quick backwards chain rule u substitution. So I'll let u equal the entire denominator, in which case we get du is equal to 2x dx. Dividing by 2 allows for a nice substitution here, integral of, or 1/2 the integral of 1 over u du. The antiderivative is 1/2 ln of the absolute value of u, but the absolute value can be killed because 1 plus x squared is always positive, so we can get rid of the absolute value and just have the expression 1/2 ln of 1 plus x squared. So that's the antiderivative, and now I'm just going to pull it back into the answer, and I have my successful antiderivative. So pulling it back in, I have x arctan x, I have minus 1/2 ln of 1 plus x squared, and I should put my plus c. So that would be the full antiderivative here. So bringing you back here, that's how I achieved the 1/2 ln of 1 plus x squared. And then I went back here and I just plugged it back into where that was. And I have found what we call an elementary antiderivative of arctangent x. You might be like, that doesn't look so elementary, but it is. Elementary means you're using the functions that you learned from pre-calculus, whether they're algebraic or transcendental, which these are, arctangent and ln are transcendental, but nevertheless, it's considered elementary.
I have a quick question.
Sure.
Is it VdV or VDU?
So it's uv minus the integral of v du.
Okay, thank
So
you.
that could be a yes. Let me see if I can draw. uv minus integral of uv minus integral of voodoo. That's how I remember voodoo, vdu. Any questions here? Okay, now,
Bieber?
yeah, sure.
For the exam, do we need to memorize like the derivative of like tangent and like arctangent and stuff?
Yeah, so the more derivatives you know, the better. So I always say that you should definitely memorize derivatives. And we'll go through as many as we can. So through WebAssign, through here, hopefully you'll be able to practice. But the more derivatives you know, the better, because there's not that many. There's not that many derivatives.
Could we be asked for explanations for these type of questions?
No, I mean, I'm looking for the antiderivative, and for this lecture, I'll be a little bit, there'll be some more clarity on my part with some of the newer TAs that we have in terms of this. But you should always show your work. But I think there was a little bit of I think it was a little bit strict. Although I believe it was fair across the board, I think there was some strictness. So I think we're all going to have some meeting of the minds, but for the final, so it'll be okay.
Bieber?
Yeah.
Instead of arctan, can I use tan inverse?
Yeah, same thing. Arctangent and inverse tangent. There's no preference of one over the other.
Okay.
Can you go back to the final answer?
Sure.
A question.
Yeah.
So like if we were to leave the 1 plus x squared in absolute value, is that like worthy of getting a point off in like, I mean,
It's really not, but I had it. I'm once in my 25-year career, talking about strict TAs, I had a TA who took points off for that, 1 point for that. And I was like, you gotta be kidding me. But the TA was like, no, you don't do that. So I think that's a little bit much. So if you had the absolute value, it's fine. I would overrule the TA and give the credit.
Great, thank you.
All right, so let's try. This will be something. I feel like this.
Hey, Professor?
Yeah, go ahead.
Why doesn't the final answer have the absolute value, but just like the U substitution?
Yeah, because what happens is I was just saying you could have the absolute value. It's okay to have it, but it's overkill. The quantity, the expression 1 plus x squared is always positive. So having the absolute value is overkill. 1 plus x squared, no matter what, is always a positive number. So there's no need to have the absolute value. All right, so here's a question I think I accidentally asked you on WebAssign once, interestingly enough. And I had to remove it. So suppose we have the integral from 1 to infinity of n over e to the n. And we go back to our main objective here, which is converge or diverge. To be or not to be, that is the question. So here's an infinite series. And part of the reason I did this topic was, well, A, it's standard to know how to integrate by parts. But also, integration, the integral test, rather, was kind of incomplete because we weren't able to do a lot of questions because we only had one technique of integration at our disposal, namely U substitution. Well, now we can go back and do this question, which I accidentally asked you on WebAssign a few weeks ago, and we actually can invoke the integral test here. This particular integral, n over e to the n, could actually definitely be utilized with the ratio test. But if I asked you to do the integral test here, we could definitely have success. So here we're being asked to converge, whether it converges or diverge. So I'm about to use the integral test here. And again, the integral test can be used if the function here is decreasing, which it is. So what I'm going to do in order to get the answer to this question using the integral test is to actually temporarily look at the indefinite integral, integral of x e to the negative x dx. So first of all, I'm replacing the n here with the real variable x, and I have integral of x e to the negative x dx. So again, I got rid of the fraction and I brought this to the top and made it e to the negative x. So this is an indefinite integral. This is similar to what you had on the midterm. The only difference now is you can't use u substitution. You're going to wind up using integration by parts. So why don't we do this piecemeal? Why don't you do integration by parts here? And then we'll see what happens. So try integration by parts here, just on this guy. And then we'll make progress towards the end of the question. So try voodoo here. All right, so let's do our integration by parts here. So we have our u as u is x, dv is e to the negative x dx, du is dx. Now here's the interesting part. This is e to linear. So this is very similar to what happened with the sine and the cosine. I would not do a full-blown u substitution here. This is e to linear. So the antiderivative of e to something is e to something, but you would take the reciprocal of the linear coefficient. Reciprocal of -1 is -1. So your antiderivative is actually negative e to the negative x. I would memorize the antiderivative of e to the negative x is negative e to the negative x. If you're going to take any more math classes, this is going to come up many, many times. So you want to know the antiderivative of e to the negative x is negative e to the negative x. Can you see the board?
Yes.
Okay. Okay. So then we wind up having here uv. So tell me if we lose the board. uv is x times negative e to the negative x is negative x e to the negative x, uv, minus the integral of voodoo. So minus the integral of voodoo is a plus e to the negative x dx. The minus.
The writing.
The writing is gone, right?
Yeah.
Okay. So we'll have to do this for the last time tonight. So I'll be back again. See you in a minute. And then this will be the last problem, but I want to finish this with you. So we will do this. I'll be right back. So let me just quickly go back here. We're doing integral of x e to the negative x dx. And in the problem, we had the u was the x, the dv was the e to the negative x, du is equal to dx, and the v here is negative e to the negative x. So now we have the uv, negative x, e to the negative x, that's uv, minus the integral of voodoo. So that became plus the integral of e to the negative x here, dx. Well, once again, negative x, e to the negative x, you want to know the integral again, same antiderivative again. That becomes minus e to the negative x. So plus c if you want. There's the full antiderivative. That's the full antiderivative right there. So we're going to use this antiderivative now in the integral test. So we have the antiderivative by integration by parts, negative e to the negative x minus e to the negative x plus c. And now we've got to go back with the improper integral. So we have the integral from 1 to infinity of x e to the negative x dx. And of course, we need the limit as L goes to infinity, integral from 1, maybe we used b in this class, I beg your pardon, it doesn't really matter. B to infinity, integral from 1 to b of x e to the negative x dx. And now I get to use what I found. Limit as b goes to infinity. And we have our antiderivative, negative x e to the negative x, 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 negative x e minus e to the negative x. And we don't need the plus c because it'll cancel out. And we're going from x equal 1 to x equal to b. So here we go with the fundamental theorem of calculus, f of b minus f of a, limit as b goes to infinity. We have here negative b e to the negative b minus e to the negative b. So that's what we have here. So I'm going to put big brackets. And then minus, we have negative 1 e to the negative 1 minus e to the negative 1. So this is me writing it out verbatim here. I just substitute in the upper limit of integration and the bottom limit of integration. Question now becomes, what happens to that first limit here? So trying to make heads or tails of this, keep in mind here that this really is the same as negative b over e to the b. And this here is just minus 1 over e to the b. So as b gets infinitely large, this and this go where? Anybody know? 0. So you could do this. You could do this one by L'Hopital's rule if you want, but you realize that e to the b is growing much faster than b. So this is going to wind up going to 0. This goes to 0. And then we're winding up with a finite answer here using the distributive property. We get plus 1 over e. That's that part. And then we wind up getting plus 1 over e. Okay, this is actually pretty interesting here. And we wind up getting just 2 over e. Now, some people in the midterm lost credit with from one of the TAs because, they said that the series converged to 2 over e. That's not true. The integral converged to 2 over e. The integral converged to 2 over e, which just tells us that the series converges. We don't know what the series converges to here, but because the integral converges via the integral test, we know the series converges. But the area under the curve, if I drew this curve and I tried to find the area from 1 off to infinity, despite the fact that it's unbounded, we still have a finite area under the curve, namely 2 over e. Okay, questions here? All right, everybody. Stay safe in the storm if you're on Long Island. And homework will be posted on Thursday. And next week we'll be wrapping up series with a hodgepodge of different things, but I listed mainly the things in the syllabus if you wanted to get a head start. So have a good week, everyone. If you want to come back Thursday, of course you can to see me do pretty much the same thing. Otherwise, I'll see you next Tuesday.
Bye, Bieber.
Bieber, could you go back a slide?
Sure. Take care, everyone.
B-Burn?
Yeah.